The universe is bound by a fundamental limit on speed, the speed of light. This restriction defines how far we can see, setting a boundary on our observations known as the cosmic horizon. We can only observe objects and events within a certain distance because light from farther away has not had time to reach us. The diameter of the observable universe is estimated to be about 93 billion light-years, which seems paradoxically vast given the universe's age of approximately 13.8 billion years. This apparent discrepancy arises because space itself has been expanding since the Big Bang. Regions that were once close together have drifted apart due to this cosmic expansion, and the light from these regions has taken longer to reach us. Thus, even though the universe is 13.8 billion years old, the stretching of space has effectively expanded the distances between celestial objects, enlarging the observable universe far beyond what one might expect if space were static. Despite all we have learned, the universe remains profoundly mysterious. With every discovery, we deepen our appreciation for its complexity and grandeur. Tools such as NASA's James Webb Space Telescope, JWST, and other advanced instruments allow us to probe these mysteries further. These telescopes help us study a range of cosmic phenomena, from the life cycles of stars to the evolution of entire galaxies, offering unparalleled glimpses into the structure, composition, and history of the cosmos. As scientists continue to push the boundaries of exploration, they make astonishing revelations about the farthest reaches of the observable universe. If you want to stay updated on these breakthroughs, following the latest news is essential, as new findings can transform our understanding of our cosmic neighborhood overnight. Beyond the observable universe lies an even more challenging question: what exists in those regions we can never see? This question forces us to confront the limits of current scientific knowledge and invites bold speculation about realms forever beyond our direct reach. To explore those farthest reaches would demand technology that can transcend space-time itself, ideas like distortion drives or traversable wormholes. These concepts, while staples of science fiction, remain highly theoretical. Some physicists argue they are impossible under our current understanding of the laws of physics, particularly the cosmic speed limit set by light. Even if faster-than-light travel were theoretically feasible, the technological sophistication required would vastly exceed our present capabilities, demanding a level of engineering and energy manipulation we can barely imagine. Among the most profound theories in modern cosmology is the concept of cosmic inflation. This theory suggests that the total size of the universe is at least 10 squared cube times larger than what we can observe. Such a number is so unimaginably vast that it defies our intuition. Because light from regions beyond our cosmic horizon will never reach us, we cannot observe or measure these regions directly, and so we can only theorize about their properties. Yet despite this limitation, scientists can build compelling and rigorous theories grounded in the data we do have, such as the cosmic microwave background radiation and the distribution of galaxies across space. These observations give us indirect evidence about how the universe evolved and hint at what might lie beyond. NASA, along with other space agencies and research institutions worldwide, has played a crucial role in expanding our knowledge of the universe. Even before the JWST became fully operational, NASA had released breathtaking images of the cosmos with a Hubble Space Telescope, such as the Hubble Ultra Deep Field, which revealed thousands of galaxies in a tiny patch of sky. But when the James Webb Space Telescope launched, it promised to look even farther back in time. Its infrared capabilities allow it to see the stretched, redshifted light from the earliest galaxies, giving us a window into the universe as it appeared just a few 100 million years after the Big Bang. The first images from Webb confirmed that it could detect the most distant galaxy ever recorded, pushing our observational limits and opening new frontiers for studying the early universe. Webb's ability to detect infrared light is vital because as the universe expands, the light from distant galaxies is stretched to longer, redder wavelengths, a phenomenon known as redshift. By capturing this light, the JWST can peer deeper into the cosmic past than ever before. Early observations revealed countless galaxies shining in the distant reaches of space, some of which appear as they were only a few 100 million years after the Big Bang. These deep-field images show galaxies forming during the universe's infancy, helping scientists study star formation rates in the early universe and understand how galaxies evolved over cosmic time. The data has already revealed a surprising population of galaxies forming stars at unprecedented rates, challenging existing models of galaxy evolution and painting a richer, more complex picture of cosmic history. Such discoveries provoke profound reflection on humanity's place in the universe. For generations, people have looked at the night sky and wondered whether we are alone. With every new observation, the possibility that life exists elsewhere seems increasingly plausible. Scientists and philosophers alike now consider it likely that there are millions, if not billions, of galaxies beyond our observable horizon, regions forever inaccessible but no less real. This idea is both astonishing and humbling, reminding us how small and fragile our own world is within the vastness of the cosmos. It also deepens the mystery of whether life exists elsewhere, perhaps even intelligent civilizations, waiting to be discovered. The hunt for life beyond Earth has grown increasingly sophisticated in recent years, particularly through the study of exoplanets, planets orbiting other stars. Thousands of exoplanets have been discovered using methods such as the transit technique, which detects dips in a star's brightness as a planet crosses its face, and the radial velocity method, which measures the tiny wobbles in a star's motion caused by an orbiting planet's gravitational pull. Some of these exoplanets lie within their star's habitable zones and possess conditions thought to be suitable for life as we know it. Among the most remarkable recent discoveries was made with the help of the JWST, which analyzed the atmosphere of an exoplanet named WSP-96b. This planet lies outside our solar system, and its light spectrum revealed the presence of water molecules in its atmosphere. Even more intriguingly, the analysis detected haze and clouds, features that had once been considered unlikely or even impossible for potentially habitable planets. These findings suggest that our solar system is unlikely to be unique in its ability to support life. The diverse range of potentially habitable environments in our own solar system, from the subsurface oceans of Europa and Enceladus to the possibility of life in Mars's ancient past, supports the idea that life might be common wherever the right conditions exist. As our methods for detecting and analyzing exoplanets improve, it becomes increasingly difficult to dismiss the possibility that alien life exists beyond our small blue planet. While we do not yet have definitive evidence of extraterrestrial life, each new discovery strengthens the case that its existence is not only possible but perhaps even likely. Beyond the question of life on other planets lies an even stranger and more speculative idea: the concept of the multiverse. The multiverse hypothesis suggests the existence of multiple, perhaps even infinite, universes or dimensions beyond our own. This idea is often discussed in the context of quantum physics, which deals with the strange and probabilistic behavior of particles at the smallest scales. One interpretation of quantum mechanics is that observation causes a quantum system to collapse into a single, definite state. But in the many-worlds interpretation, each possible outcome of a quantum event actually occurs, branching off into separate, coexisting universes. This mind-bending concept implies that every decision, every quantum interaction, could create a new universe. While the multiverse is a fascinating idea that has inspired countless thought experiments, it remains highly speculative. There is no direct evidence supporting its existence, and many scientists are skeptical of its scientific value. Nevertheless, it offers a potentially useful framework for explaining phenomena that are otherwise difficult to reconcile, such as the fine-tuning of physical constants or the paradoxes of quantum measurement. Given our ignorance about what lies beyond the observable universe, the multiverse hypothesis remains one of many plausible, though unconfirmed, possibilities, alongside other mysteries like the nature of dark matter and dark energy. These are concepts that provoke deep philosophical questions about the nature of reality itself and our place within it, even if they remain beyond our ability to test conclusively for now. Another intriguing and controversial idea is the phenomenon known as dark flow. First proposed in 2008, dark flow is a hypothesis suggesting that certain galaxy clusters are moving faster than expected in a particular direction, potentially influenced by something beyond the observable universe. The idea is that these clusters might be feeling the gravitational tug of a massive unseen structure, such as an enormous concentration of dark matter or some unknown aspect of the cosmos exerting a directional pull across space. While some studies initially suggested dark flow might be real, subsequent observations have cast doubt on its existence. The concept remains contentious within the scientific community, with no consensus about whether it is a real phenomenon or simply an artifact of measurement or interpretation. These debates exemplify the dynamic and ever-evolving nature of science. As we continue to observe the universe in ever greater detail, new data can confirm, challenge, or overturn existing theories. In the end, our quest to understand the cosmos is a profoundly human endeavor, driven by curiosity, imagination, and a relentless desire to know more about where we came from and what lies beyond. Even as we confront the limits of observation and the fundamental constraints of physics, the universe remains a vast and awe-inspiring frontier, one that will likely continue to surprise and humble us for generations to come. Even as our instruments grow more powerful, there will always be mysteries we cannot reach directly, prompting us to rely on creative theorizing and careful inference. This spirit of exploration lies at the heart of astronomy and cosmology. The more we discover about the universe, the more we realize how much remains unknown. Questions about the true shape and fate of the cosmos, the behavior of dark energy, and the ultimate origin of the laws of physics themselves continue to challenge our understanding. Some scientists speculate that future generations may develop revolutionary theories uniting quantum mechanics and general relativity,